we've been talking about different types of chemical equations this year. We classified them. For example, we had a single replacement reaction. What's another class of reactions that we've had? Double replacement. In both single and double replacement, the reaction only went in one direction. So reactants react with one another until at least one of them was consumed entirely. The reactant that is consumed entirely is the limiting reactant. And they reacted to form product, where the limiting reactant determined how much product that you generated. What you're going to see today is a different type of reaction where it doesn't only go in the forward direction. You're too noisy in the back. Whisper. For example, in a single replacement reaction, magnesium reacts with hydrochloric acid to generate magnesium chloride and hydrogen gas. Single replacement reaction, it only goes in the forward direction because magnesium is of higher activity than hydrogen. Other examples of reactions that go to completion. For example, if you have hydrochloric acid and you dilute it with water, you'll generate chloride ion and hydronium ion, and you can measure this by conductivity. The solution conducts electricity, indicating that you have ions that are free to roam. This is a reaction you've done previously where you react sodium chloride with silver nitrate. You generate sodium nitrate and this white precipitate, silver chloride. And you've done this lab previously, and in your Le Chatelier's principal lab that we will probably hit on Friday, you will be doing an experiment in which you also generate a precipitate. So when you generate a precipitate or you show you have great conductivity, the reaction essentially goes to completion. When you generate rust, which is iron 3 oxide, by reacting iron with oxygen gas, again, you'll see each balanced equation here shows a single arrowhead in the forward direction, signifying the reaction's only going in the forward direction and it goes to completion. But not all chemical reactions do go to completion. Sometimes reactants are left over, and sometimes products can react with one another to reform the reactants that initially formed them. And instead of writing multiple equations now, we do something that allows us to write a reversible equation. So you've got brown nitrogen dioxide gas. It can react with itself to form colorless dinitrogen tetroxide. This dinitrogen tetroxide can break apart and reform the nitrogen dioxide gas that initially formed it. You can figure out whether the forward or reverse reaction is occurring based on the color of the gas you have, which I'll show you. And instead of writing two reactions out, you can write a reversible reaction in which you have this double arrowhead here. Now, I typically write it that way. You'll see it a lot of different ways, and when you get to the remedial quiz, I could only make it one way. So this signifies a reversible reaction. I've also seen it drawn this way, and sometimes you'll see it written more like this. I don't like this because it's a little confusing in regard to resonance structures, etc. But typically you'll see it like this in the classwork. The only place in the remedial quiz I had to do it like that. But a reversible reaction is one that goes forward and backward. And what you'll see is when the rate of the forward reaction is equal to the rate of the reverse reaction, you have chemical equilibrium. And that's what we're going to get into today. I do want to show you the video that shows this reversible reaction where you go from brown nitrogen dioxide to colorless dinitrogen tetroxide. And you'll see that here.
We start this experiment with 3 tubes containing red-brown NO2 and colorless N2O4 in equilibrium. First, one tube is placed in hot water. A second tube is placed in cold ice water. After a few moments, we note that the tube in hot water has darkened in color. It now contains more brown NO2 than the tube which we kept at room temperature. The tube in ice water has less brown NO2 in it. It is much paler because the equilibrium has shifted to favor the formation of colorless N2O4.
So in this case, you can tell if the forward or reverse reaction is favored based on the color of the gas. And we will get into whether the reaction is endo or exothermic when we talk about Le Chatelier's principle. First thing up is that you again have a reversible reaction, which means both of these substances continue to react. So nitrogen dioxide reacts to form dinitrogen tetroxide. Dinitrogen tetroxide will break apart to reform nitrogen dioxide. It goes back and forth and back and forth and back and forth continuously. Where are you guys going? Don't get caught. I know the pass. You're going to get me in trouble. The two reactions occur at equal rates but in opposite directions. And we say that the reaction is in a state of chemical equilibrium when the rate of the forward reaction is equal to the rate of the reverse reaction. And we talked about rates of reaction in the previous lesson when we talked about kinetics. What we want to look at is what happens to the concentration of reactants and products as equilibrium is approached. And again, equilibrium is when the rate of the forward reaction is equal to the rate of the reverse reaction. So we can diagram this out as follows. Here's your balanced equation. Initially, all you have is nitrogen dioxide, shown here at some concentration. As the reaction goes in the forward direction, the nitrogen dioxide is consumed until a certain concentration at this point in time is reached. Initially, how much product do you have? None. And that's why you start here. And this concentration over time or rate will increase until it plateaus and you have a constant rate. When the rate of the forward and the reverse reactions are equal, you're at a state of chemical equilibrium. So there are several things you can draw from here. You know this in terms of the equation as written as a product, because initially you don't start with any, and you see that the rate is increasing over time. And initially you can see the rate of the reactant is decreasing over the time, or you can see it in regard to decreasing concentration over time, etc. This one's a little more informative because you can really analyze the reactants in regard to the stoichiometric coefficients. So this is the formation of ammonia from nitrogen gas and hydrogen gas. And you can see the reactants in green and blue. And what's happening to their concentration over time? They're decreasing as you would predict. And why is this, the hydrogen gas, considerably higher than the nitrogen gas? What do you mean more of it? Stoichiometrically. And that's where you were driving and everybody helped you out. So you've got a 3-to-1 mole ratio. How can you tell that ammonia is being generated? Go ahead, Jason. its concentration is increasing over time. You started with nothing and you're generating it. And you also can see that you don't have a 1-to-1 mole ratio of nitrogen gas to ammonia. Another example of a reversible reaction is one that maybe, Chris, you can tell us more about, because this is recharging of an automobile battery. So in the forward direction, this is when you turn the ignition. You have lead 4 oxide, and sulfuric acid. And sulfuric acid is the acid in a battery, right? All right, you don't want to spill that on you. That's nasty. It generates lead 2 sulfate, water, and energy is released. So is this an exo or an endothermic reaction in the forward direction? Exo. So delta H is negative. So what happens when you jump start the car? Go ahead, Chris.
Energy from another car battery is put into that battery.
Right, so you need energy from another battery to drive the reaction in reverse and then hope that it goes back in the forward direction and it stays on, I guess is the best way to say it. So this also, similar to the way you just recharge some of the batteries that you put like in the clock in the back, I stuck a rechargeable in there because this way once it is dead I can just recharge it and you can keep running the reaction in forward and reverse. Additional examples. One thing that we find with chemical equilibrium is not a static process. It doesn't stop. When you say the rate of the forward reaction is equal to the rate of the reverse, you don't say that you reach some point and everything just stops. It continues on. Think about it if you go to a ball game, football game, concert, etc. Not everybody's sitting in their seat at the same time. There are people in the bathroom, there are people getting food, people getting drinks. There's constant movement. Think about our parking lot in the morning and the afternoon. People in, people out, people in, people out. So continual. If you've ever sat there and watched bees go in and out of a hive, it's not like the bee movie where they go in, sit on the couch, watch TV. They're going in, they're coming out. How do you know? Do they have little TVs in their hives?
Oh, yeah, he's so cute. I don't like bees.
Great. Bees need a GoPro. So in and out, in and out. It's a very dynamic process, not a static process. Now in the graphs that we've looked at concentration changes over time, but you can look at mass, you can look at changes in temperature, pressure. We're going to look at color. You also can look at conductivity, but our lab will be very, very cool because we'll start with pink reactant and we'll generate blue product. And what do pink and blue make? Purple. And at equilibrium then, you're going to see that purple color. So it'll work really nicely and we'll explore that in the lab. What we want to learn how to do today is show you the relationship between reactant and product concentration. And this is very, very, very simple. So the equilibrium constant, abbreviated KEQ, K for constant, EQ for equilibrium, is a relationship that shows the concentration of reactant and product. If you have this general equation where A and B are reactants, C and D are products, just like you saw in the previous two chapters, the lowercase letters again represent the stoichiometric coefficients. Your equilibrium constant expression looks something like this, where you have KEQ is equal to concentration of products in the numerator raised to their coefficients. And you don't add these, you multiply it. So it's the product of the product concentration. In the denominator, you're going to have the concentration of the reactants raised to their coefficients. Now be careful here. It's the product of the product concentrations raised to their coefficients. It's the product of the reactant concentrations raised to their coefficients. So in the numerator, you have products. In the denominator, you have reactants. And the exponents represent the coefficients. Just remember pot, products on top. In the equation in which phosphorus pentachloride is generated from phosphorus trichloride and chlorine gas, this is a reversible reaction. At chemical equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction. So initially, you've just got reactant, and the phosphorus trichloride and chlorine gas will react to form product. Then as the reaction goes, the forward reaction is going to slow. When the phosphorus pentachloride is generated, it will bust up, and its reverse reaction will increase until equilibrium is reached. KEQ is equal to the concentration of product over the product of the concentration of reactants. Two important points here that I want to make, and we'll come back to them again and again. The value of KEQ is temperature dependent. If you alter the temperature, you alter the value of KEQ. Temperature is the only factor that alters the value of KEQ. When you write KEQ expressions, the only states of matter that you include are gases and aqueous substances. You do not put solids or liquids in an equilibrium constant expression ever. Their concentrations are constant and they are excluded from KEQ. Let me show you how to write KEQ expressions. It's very, very, very simple. Do you guys have your notes or no?
No.
No? All right. So in the first equation, I'm rewriting it here since you're so prepared for class. Here's your reversible reaction. How do you know this is a reversible reaction? The double arrow. What it's asking you to do here is write the KEQ expression. You write KEQ. Don't forget the KEQ. K for constant, EQ for equilibrium. What goes on top? Product or reactant? So brackets for concentration of the product, and I'll raise it to what power? 2 because of the coefficient of 2. Now reactants. Sulfur dioxide raised to what power?
2.
Oxygen.
1.
Done.
That's so easy.
I told you it was easy, but you don't believe me.
Yeah, because you always say it's easy.
I know, because it is easy.
You know you have a doctorate. It's like teachers said the tests are easy. Yeah, because they have the answer.
All right, number 2. It's very noisy in here.
It's AP Chem.
Shh.
She flunked AP Chem. Me too.
All right. What's the KEQ expression for number 2? Chlorine gas raised to the
2.
water raised to the
2.
Now be careful here. Let me reiterate that this is the product of, don't you dare add those. That will be a bomb, bomb, bomb. Sam, can you please stop playing with her hair? All right. What goes here? What exponent? What goes here? All right. Number 3 is a little tricky. We'll do 3 together. Oh, we're getting to the math. You know it's coming.
Is that tomorrow's lesson?
right, number 3 is a little trickier. What did I tell you about the only states of matter that go in KEQ expressions, Sam? They do have to be gases or aqueous, so no solids, no liquids. Carbon monoxide, carbon dioxide. Why don't we put the carbon in? It's a solid, so it's part of the balanced equation, but it's not part of our equilibrium constant expression because their concentrations don't change nor their activities, so they're excluded. All right, you try number 4. Go! I put it on the screen, sillies. Actually, you're going to do the reverse reaction of that in the lab, and that's why I give you this crazy one. Can we focus?
It's just trick. It's so tricky.
It's at the top of the screen. Yes, darling.
CO and H2O would be separated, right?
Nope, that's just an ion. It's a complex ion. They have pretty funky names, so I'm not going to go into the naming of them, but they're complex ions. Yep. It's going to look like this. This is a complex ion. It's a cobalt-2 ion with 6 water molecules. Where's the blue bag?
I think about that.
I did. I had all the cookies in there.
I took a cookie bag, and then now I don't know where it is.
All right.
You should have brought it. That wasn't me.
So the whole ion concentration, chloride ion, why did I raise this to the 4th?
It's coefficient.
Coefficient as such. What happened to the water? It's a liquid. All right, so Allison said, that's it. And of course she knew that wasn't it, because now that we know how to write these, now we have to solve them. So if I give you concentrations, you can give me KEQ. We've got 2 examples. Let's take a look. So if the concentrations of reactants and products are provided, you can calculate a value for KEQ. Now, the unit for KEQ is equation dependent. As a result, to make things easier, chemists just don't use a unit for KEQ. So you will have a unitless value for KEQ. No unit for KEQ.
I'm going to take a guess and say that later in the chapter that determines the individual concentration.
You're right. You're so smart.
What?
He said he's guessing that eventually we'll have to determine all the concentrations in there. Or just one of them, really. But any one you'd be able to do. It'll be awesome. All right, let's take a look. I'll just rewrite this since you're so prepared. It says use the corresponding equations, that should be chemical equations, and concentrations of reactants and products to calculate the value of KEQ. All right, so the first one given is hydrogen gas plus iodine vapor in a reversible format to generate hydrogen iodide gas. The concentration of hydrogen gas is 9.1 times 10 to the negative 3 molar. The concentration of iodine vapor is 5.9 times 10 to the negative 4 molar. And the concentration of hydrogen iodide gas is 0.0173 molar. And we are asked to calculate the value of KEQ. Whenever you're asked to calculate the value of KEQ, you first write the equilibrium constant expression, products in the numerator raised to their coefficient, over reactant concentration in denominator.
Are they gonna like trick you and give you the like if it's a solid, are they gonna give you the concentration?
Yes, they could. They could give you it, and you just pretend like it's not there.
Okay. Well, you know, yeah.
Yes, because it's also there.
Hydrogen iodide is 0.0173 squared. 9.1 times 10 to the negative 3 molar. 5.9. So we're just plugging and chugging away here. Just be careful with your calculator. Katie, what is with you today?
Being so fresh.
I'm not being fresh.
The one thing you need to be extremely careful with, is that in your calculator you will need those pink parentheses. If you have the multi-view, you probably need all the parentheses. Take a minute and calculate it. Make sure that you can use your calculator successfully. You don't want to make a silly mistake. Make sure you got what I got.
Is there no like because the moles all cancel out?
They actually, in this case, the molar, and I didn't put a capital M here and should have, do cancel, but they don't always cancel. We don't use a unit for KEQ. Did you get 56? Yes, yes? All right, like I said, the parentheses you need are the pink ones. So in your calculator, 0.0173 squared divided by open parentheses 9.1 EE negative 3 times 5.9 EE negative 4 close equals. Do you want to try the next one, or you want to do it together?
Let's do it together.
Try it. Here, the green one, go for it. I'll do it too. 56.
Okay, that says question 2, right? So it's not like the 2 in front of the...
It's the green one.
But it's not like the 2 in front of... Okay, never mind. It's not a coefficient. It's not a coefficient. It's not the stoichiometric. Like,
Correct.
okay. That thing. I lost my entire pencil pouch.
No, that's just number 2. None of the coefficients are in parentheses like that. No.
I lost it. Or an ace paper.
I got 30,400. Dr. Page,
Yep.
30,400.
Really? You're that? You like that? He told us all the answer. I'm still trying to do my calculation. Katie, be quiet. You're not even trying. What are you talking about? You just turn it randomly and you figure it out.
I got this.
Wait, I'm not looking up. Don't say it.
Did you get that? And in regard to your question, Sydney, see in this one you get M, capital M to the -2. That's why no unit for KEQ. You just want 2 sig figs.
Hey, don't be fresh.
Huh?
I didn't get that.
Here, arrow up 3. Do you have a button like this? I'll fix it for you. Do you have that kind of button? Which calculator? Hold it up.
Okay, I'm not getting that.
Do you have like a Y to the X button?
Oh, that's why. Let's try again.
I'm not getting this. Yeah, I do.
I'm so happy. I'm sorry. Oh, wait. Just 30. It's okay. I'll figure it out. She won't go on my water bottle. The other problem is I could take it all the time. Oh, wait, what's it? Can you give me a cup? Oh, see, that's why you get one. That. Duh. Try it. Squirt it, idiot. Oh, no.
All right, calculating KEQ looks pretty good.
No, I can't. I can't do it with my calculator.
Wait, is that an approximate answer?
Well, you get 38,411, but you need 2 sig figs. 2 sig figs. All right, one last thing, guys. We'll save the harder piece for tomorrow,
Oh, thank you.
but we know that KEQ is equal to product concentration over reactant concentration. Shh. 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 Now, if KEQ is greater than 1, what has greater concentration, product or reactant? And if product concentration is greater than reactant concentration, would you say that the forward reaction is favored or the reverse? Forward, because that's how you'll make more. Now, if KEQ is less than 1, then the reactant concentration has to be larger. Now, you can't get a negative KEQ, so you're talking about a fraction less than 1 or times 10 to a negative exponent. So here, reactant concentration is greater than product, so now you've got more of this, so the reverse reaction is favored. Now, what if KEQ is equal to 1? What can you say about these two concentrations? They're equal. And here's your state of equilibrium. So if KEQ is greater than 1, the forward reaction is favored. If KEQ is less than 1, the reverse reaction is favored. And when it's 1, you're at a state of equilibrium. What you'll also see, but won't be required to know, is at equilibrium, delta G will be 0. And we talked about delta G in a previous chapter. So from the two problems that we did, with the KEQ of 56, is the forward or reverse reaction favored? Forward, because KEQ is greater than 1. What about this one? Forward. So an example of this one might be like 3.0 times 10 to the negative 4. When you've got that negative exponent there, then the reverse reaction is favored. What we'll get into next time is a little bit more of this, and as Jason alluded to, you'll be given KEQ and concentrations of 2 or more, and then you'll need the concentration of the missing. So tomorrow's lesson will be very, very short. We'll do a lot of practice, and you'll get more practice in. In regard to what we've done today, I'm going to give you classwork 4.3. You can do numbers 1 through 4 only, although I'm sure some of you could figure out the other pieces. And we'll pick up with a very short lesson tomorrow, unless we also set up the next piece. I haven't decided, but I want to make it so that you have a full day of in-class practice prior to your quiz, such that you really wouldn't have to do much studying at home. So what you picked up today, you know how to write equilibrium constant expressions, you know how to solve them, you know how to interpret them, and chemical equilibrium is when the rate of the forward and the reverse reactions are the same. I've started to go through and rewrite your 9-week syllabus, basically, just so you know when everything is. I may have to tweak a few things. I don't see much of a problem in here. All right? Questions? Okay, I'm going to get your classwork to you, and you can do 1 through 4.